This is multivariable calculus, and in this video I'm going to talk about sections 14.7 and 14.8. In section 14.7, we're going to talk about maximum and minimum values. And in this section, to start with, really thinking back to 2D calculus, we had the idea of a local maximum or a local minimum, and we understood the definition that it was sort of the highest point over some restricted domain. And when we work in 3 dimensions, the same rules apply. So we can find a local max or a local min when we're working in a 3-dimensional setting in a very, very similar way. So just like everything we've been talking about as we've been dealing with partial derivatives and using them in applications, a lot of this has very close parallels to what we did in 2 dimensions. Okay, so when we are looking for extreme values in 2 dimensions, the first thing we typically do is we find the critical points. And when we're looking for critical points in 3 dimensions, it's the same thing. We look for critical points. Now, critical points are defined slightly differently in 3 dimensions, and we saw this a little bit earlier. But we have 2 different ways of finding critical points. There's one that really tends to show up for us, which is if our x partial and our y partial are both 0 at some point, then we've got a critical point. But it's also possible we might have one or both of those partial derivatives fail to exist at a point, and that would also be defined as a critical point. So for us, typically, it's going to be the situation, our critical points are going to be when is the, or what's the point where the x partial and the y partial are both 0. Okay, so let's take a look at a quick example. It says, let f of xy be x squared plus y squared minus 2x minus 6y plus 14. Find the critical points of the function. So this is very easy to do. There's not really a ton of steps here, and this is very similar in process to what we did before back in 2D calculus. So here's my x partial. If I set that equal to 0, I'm going to find that x is equal to 1. So that's going to be potentially my x coordinate for my critical point, assuming that I can find a y value to correspond to that. So for my y partial, when I take my partial derivative, I get 2y minus 6, set that equal to 0, and we get y is equal to 3. So we do have a point where both the x partial and the y partial are both 0, and it's the point 1, 3. So I'm just going to use CP for critical point, and in this case, it would be the point 1, 3. Okay, so there's my critical point. Now, just like before, when we were looking for our maximum or our minimum values, once we found the critical point, there were other things we could do. We had things like the first derivative test, we had the second derivative test, and then if we had a closed interval, we looked at critical points and endpoints. So all of those same rationale are going to apply here. Before we get there, though, let's just take a look at, everybody kind of knows what a max and min value is. In 3 dimensions, though, we have one other type of point that sometimes will show up, and it is called the saddle point. So essentially what we have at a saddle point is that if I look at this graph, and if I'm approaching it from one direction, it looks like a maximum point. But if I approach it from another direction, it looks like a minimum point. So that is referred to as a saddle point. So in addition to finding max and min values, we're also going to identify saddle points. Okay, so here's a quick graph of the idea of maximum and minimum values when we're dealing in 3 dimensions. And you can see that we've got the same basic definitions. I can have a relative max or a relative min or a local max or a local min. But then if I want to call something absolute max or an absolute min, it has to be the highest point on my entire, what we would have said before was interval, but now we're talking about an entire region of points. So my absolute max in this case is the highest point on this region. It looks like sort of like a square region. I guess it is a square region that we have defined here. And my absolute minimum would be my lowest function value on that same square region. Okay, so what we typically use when we're looking for maximum and minimum values, this is the most common test that you're going to see. It's called a second partials test. And this is, again, very much like stuff that we did in 2D. If you think back to the second derivative test, remember that was all based on concavity. If we found the point where a slope was 0 and then we tested for the concavity at that point, we could figure out if we had a max or a min if it was in fact an extreme value. And in this second partials test, we're going to use similar reasoning. It's a little more complicated though, because now we have to take into account the fact that we've got more things going on from a concavity perspective. So this is the way that it works. When we are doing a second partials test, we sort of need to account for concavity in all directions. So like we just saw with the saddle point, you can be concave up in one direction and concave down in another direction. And so you might end up with kind of weird scenarios where you're not just using like the idea that concave up means a minimum and concave down means a maximum. So what we do is sort of take like a preponderance of all of those concavities and see if we have a consistency. And if we do, we can define a maximum or a minimum. And that's what this second partials test is based on. Now, this second partials test is actually, in the end, a determinant of a 2x2 matrix of all of our second partials. And it sort of gives us an end result of, okay, do we have consistency in our concavities from the different directions? And remember, there's an infinite number of directions I can be looking at from a concavity perspective. So that's what this sort of encompasses. Now, the idea behind this and proving all of this is really beyond the scope of this course. You can see that obviously, since we're doing a determinant, we're starting to getting into the idea of maybe using some linear algebra to prove this. But we're just going to use this and apply it as opposed to actually proving it. But some of the logic behind it, we will talk a little bit about. Okay, so what we're looking for here is we're looking for the determinant. That is our, that 2x2 matrix I was talking about. We're looking for that determinant to be positive because that's going to indicate to us that we've got consistent behavior amongst all of our second partials. So anytime that determinant is positive, we know we've got consistent behavior. Now, with that being said, if we have consistent behavior, then we have to start thinking about, okay, do we have consistent behavior where we're looking at like a concave down or a concave up situation? So if you look at these first two scenarios, you can see that I have a determinant that is greater than 0. That means I have consistent concavity. I look at my second x partial, and it's greater than 0. That means I'm concave up in that x direction. Well, since my determinant is positive, that means I'm concave up everywhere. So that means we're going to have a minimum. Same thing if the determinant is greater than 0 and the second x partial is less than 0. Remember, that would mean that we're concave down in the x direction. Well, since the determinant was positive, that means we're concave down in all directions. So that would mean we have a maximum. Now, the saddle points are going to show up when you have a determinant that is less than 0. So that's going to indicate to you that we have inconsistency in our concavities in the different directions that we can approach a point from. And then the last one is if we ever get a determinant that's 0, that means we can't draw a conclusion from the concavity, and this is not a good test to use. So there are other high-level ways of determining maximum and minimum values, not that we're going to be discussing in the scope of this course, but there are other ways that you can do maximum and minimum values that get a little beyond what we're going to do. So for us, it's going to be the second partials test when we're looking for these maximum and minimum values. So the big thing here is if you understand conceptually what we're looking for and understand that that determinant is sort of figuring out for us if we have consistency, then you don't really have to try to memorize all of this because you're sort of doing the same thing as the second derivative test. And as long as you know how the second derivative test works, then the only thing you're adding on to it is understanding what the determinant is representing. Okay, so this first question, it says, locate all relative extrema and saddle points of this function. F of xy is 3x squared minus 2xy plus y squared minus 8y. Okay, so looking at the graph, it looks like I probably have some sort of a minimum value here, and that's what I'm going to try to determine. Okay, so just like we did a minute ago, the first thing we need to do is we need to think about critical points. So I'm going to start with my x partial, which in this case is 6x minus 2y. And then I'm going to set that equal to 0. Notice that I've got two variables in a single equation here. I'm hoping my y partial is going to give me more information that I can then use to solve a system of equations. And in fact, it does. My y partial here, I'm going to get negative 2x plus 2y minus 8, set that equal to 0. So in the end, I've essentially got a really simple here system of equations. 6x minus 2y is 0, and I have negative 2x plus 2y is equal to 8. This is a system of equations that obviously we could just solve that really quickly by elimination. It wouldn't be difficult to do. But in the end, we would get x is 2 and y is equal to 6. Okay, so a lot of the algebra on these problems, I'm not going to work through steps. You guys know how to do that kind of stuff. Okay, so now we need to look at our second partials. If I look at my second x partial, I'm going to get 6. If I look at my second y partial, I know I'm going to get 2. And then remember, since we've got a polynomial equation here, my mixed partials are going to be the same. So it doesn't really matter if I get xy or yx. I'm just going to get xy. And when I do that, I'm going to end up with negative 2. Okay, so when you look at these numbers, this can be a little bit misleading because you can see that we're concave up in the x direction, we're concave up in the y direction, and then you see that fxy is negative 2. That might make you think, well, that means we've got negative concavity in these other directions. And that's not really what that's representing. So we can't really go through and look at it that way. That's where this determinant comes into play. So what we want to do is we want to calculate this determinant value at the point 2, 6. And when we calculate the determinant, you can kind of see what happens here. So I already know that I'm looking at a scenario here where I've got both my x partial and my y partial are both positive. So it's very likely that I'm going to be looking at a positive determinant, but I just want to verify that. So I'm going to do my x partial times my y partial, or my second x partial times my second y partial, and then minus this mixed partial squared. Okay, so notice that it doesn't really matter whether that second mixed partial is positive or negative because we're going to square it anyway. What does matter from the perspective of that mixed partial is the magnitude of it, because how does it compare to the magnitude of those other partials that I have? So in the end here, I got a value of 8, which is greater than 0. So that's really what I needed to know, is the determinant greater than 0. In this case, yes, it is. And that means we have consistency. We also know that the x second partial at this point 2, 6 was greater than 0. Well, if that x second partial at 2, 6 was greater than 0, that means we're looking at a situation where we have it's concave up in the x direction. The determinant being positive tells me we're concave up in every direction, which means at this critical point, we actually have a minimum value. So we can say, therefore, there's a relative min or minimum value at the point 2, 6. And just like when we were in two-dimensional calculus, depending on what they ask you for, sometimes you need to report the point. Sometimes they're going to ask you for the actual function value. It just depends on how the question is worded in terms of what information we need to supply. Here I just gave the coordinate. I could easily go through and plug the 0.26 back into the function and get the corresponding function value. But you can see that kind of matches up with what we see in this graph. We expected to get a minimum, and that is indeed what my second partials test gave me. Okay, so in that scenario...
Teachers, please take attendance at this time.
Okay, in that scenario, we only had one critical point. So it was very easy to run this test. It wasn't really confusing about trying to keep everything straight in terms of what does everything mean. Well, sometimes we have multiple critical points. And what I want to show you on this next one is just a really easy way of organizing your data and organizing your thoughts so that you can come to your conclusions without having to write out a bunch of extra work. So here's another similar type of problem. You can see that we've got a function. We're given the graph here. It looks like we've got 2 points that are relative maximum points. But I don't know anything else. I mean, it's kind of hard to see this. It's not the best three-dimensional graph. So we don't have a way to sort of manipulate that thing. So what I'm going to do here is start with critical points again. And I'm going to start with my x partial. And when I get my x partial here, it's 4y minus 4x cubed. And remember, we're going to set that equal to 0. That would give us y is equal to x cubed. And then we also have our y partial here, which would be 4x minus 4y cubed. And that would give me, when I set that equal to 0, that would give me x being equal to y cubed. Okay, with some simple substitution here, I can solve this out and I can get my critical points. And again, I'm not going to show the algebra here. You guys know how to do this algebra, but there's actually 3 critical points here. And my critical points occur at 0, 0, which that one we can just kind of look at it and know. We also are going to get the point 1, 1, and the point -1, -1. Okay, so we have 3 critical points this time that we have to account for. So that's why I said I want to sort of organize my work here to make it a little bit easier to work through this problem without having to just, grind through endless amounts of sort of trivial calculations. Okay, so the last thing we need, we're going to do our second partials test. So we're going to need our second partials. So my second x partial is negative 12x squared. My second y partial would be negative 12y squared. And then my mixed partials are going to be equal to 4. Okay, so those are the values, or those are the partials that I have. Now notice we didn't get constants this time, so it's a little bit more work, but still fairly straightforward. So what I'm going to do is I'm just going to set up a table that's going to streamline all of this. And in my table, the important information, my critical points, my second x partial at that point, my second y partial at that point, and then my mixed partial at that point, and what I really need, which is the determinant at that point. Okay, so obviously we're going to have to calculate these values for all of these mixed partials, except for for all of the second partials, except for the mixed partial, which is always a value of 4. But for my first critical point, I'm at the point 0, 0. So then, okay, what is my second x partial? It would be 0. What's my second y partial? Also 0. I know my mixed partial was 4. And now remember, we're going to do the second x partial times the second y partial minus the mixed partial squared. So we're going to end up here with a determinant value of negative 16. Okay, so notice that we got a determinant that was negative, which means that we have inconsistency within our concavities. So now I can come to a conclusion based on that. I'm not going to write down my solution just yet, but just realize the determinant being negative means we've got inconsistency in the concavities. Okay, so now we're at the point 1, 1, the next critical point. My x partial, or my second x partial has a value of negative 12. Second y partial also negative 12. And then this mixed partial is always going to be 4. And now remember, same thing when I go through and I do negative 12 times negative 12, I get 144 minus 16. That's going to give me 128. So we got a determinant that's positive, which means now we have consistent behavior. Okay, and then the last point, we've got the point -1, -1. So my second x partial, in this case, again, is going to give me negative 12. Second y partial, again, negative 12. Mixed partial of 4. And again, same thing, 128. Okay, so those determinant values are what was very, very important to me, because those are going to tell me whether I have consistency. And then if I do get a positive value, then I can either look at my x partial or my second x partial or my second y partial to determine really what's the concavity that's consistent there. Okay, so in the end, for that critical point at 0, 0, I can see I have a saddle point because I had inconsistent concavity. So I have a saddle point at the point 0, 0. And then notice with the other 2 points, the critical point at 1, 1 and -1, -1, we have consistent concavity, and both of them have a second x partial that's negative, indicating that I would have a relative max at those points. Okay, so relative max at those two coordinates. So at 1, 1 and -1, -1. Okay, so the main thing here is, I mean, this is pretty simple once you get kind of the gist of it, but use things like this to your advantage. You know, I'm really streamlining all of my work into a nice concise table as opposed to writing out every single value individually and then compiling all that information one point at a time. So it makes it much more efficient to solve a problem that has multiple critical points when you set it up this way. And notice again with our graph, we got something that's consistent from a maximum standpoint. Saddle point, it looks like maybe somewhere between those two maximums, that's probably where that saddle point occurs. Okay, so now let's take a look at maximum and minimum values when we have a closed space that we're looking at, or a closed region, I guess I should say, that we're looking at. So in 2D, when we were looking for absolute max and min, we would look at critical points and endpoints whenever we had a closed interval. Well, now when we have these closed sets of points, we have to look at critical points and we have to look at boundary points because we're working now in 3 dimensions. So our boundaries are like what were our endpoints in 2 dimensions. Okay, so the process here is kind of the same. If I want to find absolute max or min values, I know that they're going to occur if I have a function that's continuous on some set of points. All I have to do is look at my critical points. I have to look at my boundary points. Whichever one point or points is the highest, that's going to be my absolute max. Whichever point or points are the lowest, that's going to be my absolute minimum. Now, executing this is a little more complicated than it was in 2D, but it's still the same general idea. Okay, so in this problem, we are given this scenario. It says find the absolute max and min values of f of xy is 3xy minus 6x minus 3y plus 7 on the closed triangular region R with vertices 0, 0, 3, 0, and 0, 5. Now, this graph that we're given is not the graph of the function. That is the region, that's sort of the slice of the function that we would be looking at. So anywhere those function values are within that region, that's where I'm looking for the maximum and minimum values of this function. Okay, so within the region that is defined by this triangle. Okay, so now let's go through and look at our critical points. So when I do my x partial, I get 3y minus 6. Set that equal to 0, I get y is equal to 2. For my y partial, I'm going to get 3y minus 3. Set that equal to 0, I get x is equal to 1. So I have one critical point. I have a critical point at the point 1, 2. Now, remember, we have to look at critical points and endpoints, or boundary points, really is our 3-dimensional version of that. So when I look at this, my boundaries here are these lines that are the exterior or the boundaries of the triangle. Okay, so I've got the one along the x-axis, the one along the y-axis, and then I have that angle or the line that angles down through there from the 0.05 to the 0.30. So those are my boundaries. Now, what we can do on those boundaries is we can determine if we have a max or a min along the boundaries in a similar way. So I'm going to do this along each of those lines. So I have the line segment that goes from 0, 0 to 3, 0. Okay, so when I'm along that line, I know y is equal to 0 because I'm on the x-axis with those points. And that means that if I look at my function, f of x 0, because the y value is 0 on the x-axis, my function becomes negative 6x plus 7. Okay, so do I have a critical point in my function along that boundary? Well, the way I would determine that is I only have one variable here. So notice if I take the derivative, I get negative 6. That's never going to be 0. There's no critical point on that boundary. So we can't have a max or a min on that boundary line. Okay, so now let's do the same thing on the other boundary lines. So I've got the line segment that goes from 0, 0 to 0, 5. So that's the one on the y-axis. That means that x is equal to 0. So if I were to evaluate my function, it's essentially f of 0y, which is the same as negative 3y plus 7. And all I'm doing is I'm taking this function, the original function, this one up here, and I'm saying, okay, I know x is 0. That basically eliminates all of those x terms, and then I'm just left with the negative 3y plus 7. Okay, so now, same thing. Do I have any critical points along that line? Well, I only have a single derivative. When I take the derivative, I get negative 3. That's never going to be 0. I have no critical points along that line either. So I can't have a maximum or a minimum along that line. So we have one other line, and it's the one that goes from 0, 5 to 3, 0. So this is my last line segment. So from 0, 5 to 3, 0. Now the equation for that line is y is equal to negative 5/3 x plus 5. And you could figure that out pretty easily because we have a y-intercept of 5 and the slope is just rise over run. So pretty easy to get that. Now, when I plug that into my function, what I'm going to do here is I'm going to create a new function. I want to get this in terms of a single variable. If I have just x as my variable, the y, remember, is the same as negative 5/3 x plus 5. And what that gives me as a modified function when I'm along that boundary line of negative 5x squared plus 14x minus 8. Okay, so this time you can see I'm actually going to get a critical point. So I'm going to do this derivative again. It's going to give me negative 10x plus 14. Set that equal to 0, and I get x is equal to 7/5. And then from there, we can get the corresponding y value. It turns out that the y value is 8/3. Okay, so again, thinking back to 2D calculus, when we were going through and doing a max or a min on a closed interval, we did critical points. You can see we have 2 critical points here, critical points and endpoints. And along our boundary, we ended up with a second critical point that we need to look at. So the other points, though, that we do have to account for are these points that are at the very ends of each of these lines, because these are technically what we would call our endpoints, because that's where all those boundary lines are intersecting. So we have to account for those as well. Whether or not we're going to use them, we have to kind of wait and see. But we do have to test all of the possible places where you could have a max or a min. Okay, so it kind of makes sense if you think about it. I can see that what's happening along, when I went along, for example, the y-axis, when x is 0, you could see I had a negative slope all the way along that. So I can kind of predict what's going to happen with my function value when I'm looking at along the y-axis or similarly along the x-axis. But the way that we test this out and we justify our answer is by using a candidates test, just like we had done before. So rather than writing my candidates test, though, vertically, I usually write out my candidates test horizontally here when I set up my table. And it's just because when I format this, the way that these points are going to be written out, sometimes it's a little bit more concise in terms of, drawing a big long table versus having a horizontally oriented table. So here's my x, y values, and then I'm going to have the corresponding function values at each one of those points. Okay, so first of all, we just talked about all of those, sort of endpoints. So we had the point 0, 0. That's going to be one of my columns. We have the point 3, 0. And we have the point 0, 5. And then we also found those critical points. One of them was just sort of like our standard critical point at 1, 2. And then we found one of them that was along one of those boundaries. And that was at the point 7/5, 8/3. Okay, so now all I've got to do is I've got to look at my function and say, okay, what are the values at all of these points? Well, 0, 0, we get a function value of 7. 3, 0, we get negative 11. 0, 5, we get negative 8. The point 1, 2 gives us a value of 1. And the point 7/5, or 7/5, 8/3 gives us a value of 9/5. So that one, obviously, I'm skipping over all of the computations, but that one would be a little bit of work to get that exact solution. Now, so when we're looking for the absolute max or absolute min, where's our highest point, where's our lowest point in this table? Because these are the only places where the absolute max or the absolute min could occur. So we have our absolute max. You can see the highest value in this table is 7. So f of 0, 0 is equal to 7 would be my maximum. And then my absolute min. Let's see, the lowest point that I have in this table is negative 11. So f of 3, 0 is equal to negative 11. Okay, so now notice the way the question was worded. The reason I didn't just give the coordinate here, on this question it said find the absolute maximum and minimum values. They asked for the function values. So I want to make sure that as my answer, I give those function values. Okay, overall though, as far as the process goes, you can see how, again, this is basically what we did in 2D, extended into 3D, where we're now thinking about critical points and endpoints. But for the endpoints, we have to consider the boundary lines, and we have to consider if we have sort of points that have, like, if we have pieces of our boundary intersecting in a point, we have to consider those points as well. All right, so last thing here in this section. It says determine the dimensions of a rectangular box open at the top having a volume of 32 cubic feet and requiring the least amount of material for its construction. Okay, so what I want to do here is, this is an optimization question, right? So if you remember back to 2D calculus, after we understood all this stuff about finding maximum values, we started to get into application problems. Well, this is actually a really common type of 2D application problem, except here we've got 3 variables that we have to deal with, and we've got to find a way to deal with all of these variables that we have from the perspective of solving this out. Okay, so there's a couple things that I'm going to start with, and then I'm going to actually have you try this. Okay, so what we have to start with here, we know that it says we want the least amount of material. So I'm going to use S to represent, you know, my surface area, or the area of the pieces that I'm going to put together here to create this rectangular box. So I have the base, which is X, Y. I have 2 sides that would be X times Z. And I have 2 sides that are Y times Z. So I have that function. And that's really what I want to minimize. So this is the function. I'm going to put a little star next to it. That's the one that I want to minimize. But I also have other information here. I know I have a volume of 32 cubic feet. Well, that means XYZ has to be 32, because that's the volume of the box, XYZ. It has to equal 32. Well, what that's going to allow me to do is turn this into an equation of 2 variables. And I want to do that because my mixed partials, or excuse me, my second partials test is typically the way that we have learned it is done with 2 variables. So there is a way to do things when you have more than 2 variables. It gets well beyond the scope of this class and beyond a multivariable class. There are ways to deal with a sort of second partials type of test when you have more variables, but it gets way more convoluted. So we want to try to reduce this down to a 2 variable situation. So what I can do here is say, okay, well, from that, I know that Z has to be 32 over XY. And based on that, I know that I'm going to end up now with a function of 2 variables for that surface area function. And that's going to allow me to go through and sort of solve this out in a similar way. Okay, so what I want you to do then is I want you to pick this problem up from there. So we had, you know, our original function here that we're trying to optimize. And then we had the second piece is what we kind of called the constraint function, we have the constraint that x times y times z has to equal 32. That allows us to simplify this down a little bit and get it into a two variable situation. So I want you to pause the video. I want you to take a couple of minutes and try this question out. And then when you unpause the video, I'll show you my solution. All right, so let's take a look at my solution here. So you can see I rewrote my area function or my surface area function in terms of those two variables right here. And then I started going through, I got my x partial and I got my y partial. And I'm looking for critical points. So I set the x partial equal to 0. I set the y partial equal to 0, and I have a system of equations that I then solved, and I'm looking for critical points. Now, notice that I did get a point at x is equal to 0, but notice the y, first of all, the y value is undefined. And the second thing is the reason the y value becomes undefined is because if I have a 0 dimension here, I'm not going to have a volume for this box. So that's a point that's really outside of my domain. So the only point I really have to account for here, the only critical point I have is 4. Now, typically we would say, okay, let's think about critical points and endpoints. But the only other endpoints we would have to consider would require one or more of our variables to become 0. So we really don't have to think about endpoints here because any endpoint is going to have some situation where one of the variables or one or more of the variables is going to be 0. So really at this point, we just want to verify this critical point. Is this critical point actually going to give us a minimum for the amount of material required? So what I did over here on the right is I went through and I did my second partials, and then I just got the values here to check my determinant. So you can see I did my second x partial, 128 over x cubed, second y partial, 128 over y cubed, mixed partial of 1. And then I just evaluated the determinant at that point. I got 3, which means I have consistency. And then the next thing, look at my second x partial, it's positive. So I am consistently concave up at this point, which means that it is in fact a minimum. So now I've got my dimensions. X is 4, y is 4, z is 2. And I know the area then would be 48 inches squared if I go back and plug that into my original function that I was trying to optimize. Okay, so a little bit more complicated, but it's still the same thing, really. In the end, it's the same thing that we did on these types of problems where we were looking for the relative extrema and or any points that we had here. It's the same type of process, right? Now, if the endpoints were valid, then we would get into a closed interval situation and be a little more complex. But we can get into now problem solving scenarios using our partial derivatives by using this second partials test and also by using what we know about finding max and min on closed intervals. All right, so the second section that we have here is section 14.8, and we're going to talk about the idea of Lagrange multipliers. We're not going to go super in depth on this section. However, this is something that I do want you to see because it's an alternate method for finding maximum and minimum values. So remember, we talked about that whole idea that sometimes the second partials test doesn't work. This is another way that you can find max and min values. It's not the only other way, but this is one alternate method we can use. So the whole idea of Lagrange multipliers works off of understanding what happens with gradient functions. And I'm going to go through it in class. There's a graph that's in your book where they show some level curves for whatever function we're trying to optimize and then our constraint function. And wherever the function we're trying to optimize in our constraint function, if we have level curves or level surfaces for those two functions and they have an intersection point, those are the points that are interesting to us because those are our potential max and min points. Well, if we have level curves that are going to intersect, the only way that it's going to be a max or a midpoint is if our level curve for each of those are not crossing each other but are actually tangent to each other. And if our level curves for each of those functions are tangent to each other, that means their gradients are parallel. And so what we're going to do here is we're going to use the idea of parallel gradients to use that as a way to find the variables that we're looking for. So this is the method of Lagrange multipliers. We're going to say the function we're trying to find the max or min of is f, and the constraint that we're operating under is we're going to use a function g. And knowing that to be the case, like I said, I'll explain this a little bit more in class, but knowing that to be the case, then that means our gradients have to be parallel. And if our gradients are parallel, that means that this has to be true. Our first gradient has to be some scalar multiple of the second gradient. The gradient of our function we're trying to optimize has to be a scalar multiple of our gradient of our constraint function. Okay, so now where this gets a little complicated is, yes, that's a good starting point. That has to be true. But there's a lot of algebra that we have to do. Once we know that this is true, then we have to go through and we have to figure out the points where it's true by using algebra. Okay, so I'm going to show you an example, and then I'm going to have you try one of these out. So this is not super easy. From a setup standpoint, it is super easy. From a solution standpoint, it's a little bit complex. Okay, so, and I'm not going to work through all the algebraic steps, but I'm going to show you the main idea here. Okay, so first of all, we have a rectangular box without a lid is to be made of 12 meters squared of cardboard. Find the maximum volume of such a box. So this is sort of similar to the last problem that we did in section 14.7, but this time our constraint is the amount of material we have, and what we're trying to optimize is the volume. Okay, so I'm going to start by writing my function. I'm just going to use x, y, z. If you wanted to, you could draw a diagram here, but we'll just assume x, y, z are the 3 dimensions of the box. This is the function I'm trying to optimize. My constraint function, I'm just going to call it s, and that's a function of x, y, and z. And in this case, let's see, we have no lid. So I'm going to say the base is x, y, and then I'm going to have 2xz and 2yz. And I know that amount of material has to add up to make 12. Okay, so the volume function here is kind of like my f function, and the area function is like my g function. So now let me go through, and remember, we know that if I take my x partial, based on the gradients being scalar multiples of each other, my x partial has to be a scalar multiple of the x partial of that area function. So that has to be true. Well, if I get those x partials, I'm going to have yz, and I'm going to have that has to be, and this is just a lambda times 2z plus y. Okay, so I have that equation. Notice that I've got y and z and lambda in here. Okay, so now I also know the same is going to hold true for my y partial. My y partial has to be lambda times the y partial of that constraint function. So that would give me xz is equal to lambda, and if I simplify this down, I'm going to end up with 2z plus x. And I rearranged a little bit there just to make this kind of consistent. Okay, so now same thing with the third component, or the third partial derivative, the third component of the gradient. And what we have here is lambda times the z partial of the constraint function. Okay, so again here, when I do that, I'm going to get xy is equal to lambda times 2x plus 2y. Okay, so as it stands right now, I have 3 equations and I have 4 unknowns because I don't know x, y, and z, and I don't know lambda. We do have one more equation though. So remember, the constraint function itself is a relationship between x, y, and z. So my 4th equation in this system of equations is 2xy plus 2yz plus xy is equal to 12. And now you can say, okay, that's a system of equations, and let's go through and solve the system. Now, we have some different methods for solving this out. What makes this a little bit tricky is that the lambda is being multiplied. So we don't have these variables all sitting there independently. We have y times z, we have x times z, we have lambda times z, we have lambda times x, and so on. So to solve this out is not a simple process like, setting up a 4x4 system and solving it on a calculator with a matrix equation. We're going to have to do a little bit of algebraic work. And what you can do here, and I'm not going to go through this entire process, but what you can do here is kind of eliminate some of these variables by creating some consistency here. And so notice the left side of these equations. I can make all of those into x, y, z if I do this the right way. I can make the first equation x, y, z if I multiply everything by x. I can make the second equation x, y, z if I multiply everything by y. Third equation x, y, z if I multiply everything by z. So that's what I'm going to do here. First equation would give me x, y, z is equal to lambda times 2xz plus xy. And then x, y, z is equal to lambda times 2yz plus xy, and then xyz is equal to lambda times 2xz plus 2yz. Okay, so now I've got these three equations where all of them can be set equal to each other because they're all equal to xyz. So we can do some substitution and we can start to get lambda in terms of different variables here. So now what I want to do is just sort of go through here and start setting things equal to each other. Like, for example, I could take these two equations, right? And I know that these are both x, y, z. I can take lambda out of the situation entirely because now I know 2xz plus xy is equal to 2yz plus xy. And I can do the same thing with the second two equations, or the first and the third, or the second and the third. And I can start to look at individual equations and decide what's the best way for me to get x, y, and z if I can sort of remove lambda from this situation. And then it becomes a much simpler process. Okay, so like I said, I'm not going to go through all of that algebra because I want you guys to kind of play around and feel your way through it. There's more than one way to deal with the algebra, but that's the way I prefer to do it. So in the end, what you'll end up with here when you solve this all out, you'll end up with x is equal to 1, or excuse me, x is equal to 2, y is equal to 2, and z is equal to 1. Okay, so if I were to look through and kind of think about, okay, do I have a maximum or a minimum? Well, it doesn't really make sense for me to have a minimum volume because if I'm going to have this surface area, right, I could just create like a flat surface and I'd have no volume. So any legitimate points that I get have to be a maximum because when I solve using a Lagrange multiplier, I'm finding the potential points for maximum and minimum values. So since I only got 1 point, and in this scenario, my point only makes sense to be a maximum, I know this point is the maximum. If I found multiple points, I would have to just test them. Whichever one was the highest would be the maximum, whichever one was the lowest would be the minimum. Okay, so that's sort of the process that you're going to use there. Now, what I want you to do is I want you to try a similar type of question here. Find the extreme values of this function on the circle x squared plus y squared is equal to 1. This is a little bit easier because we've only got a function of 2 variables as opposed to a function of 3 variables. But overall, the process is kind of the same. So I want you to pause the video, take a few minutes, try to solve this. When you come back, I'll show you the solution. Okay, so here's the solution that I have, and I didn't show every single little step here, but the algebra on this one was actually pretty simple. So remember, we've got the function we're trying to optimize. In this case, our constraint function is that circle, the fact that x squared plus y squared is 1. So with that constraint, I just treated that as like my g. So my original function is the f, and then the constraint is the g. So I got my first partials, and then I set up the relationship based on the Lagrange multipliers. The x partials are scalar multiples of each other. The y partials the same. And I also know x squared plus y squared is 1. system of equations, 3 variables, 3 unknowns there, and then went through and just solved for the values that I get. So I got 4 points. And then since we have more than 1 point now, like I mentioned on the last problem, whichever value you get that's the highest is your maximum. Whichever value you get is the lowest is your minimum. In this case, there were 2 points that had the max value of 2, 2 points that had a minimum value of 1. Okay, so Lagrange multipliers can be a little bit complicated depending on the complexity of the algebra. But from the setup perspective, once you wrap your head around how those gradients are related, the rest of this, is all algebra work after that. So understand the concept, and then from there you can feel your way through the algebra.